Okay, so let's finish up chapter 22. We're going to continue where we left off. Remember, we were looking at beta dicarbonyls, okay? And there's basically two reactions with beta dicarbonyl nucleophiles. Okay, we looked at the first one last time. Remember, that one was the Malonic ester synthesis. And the second one that we'll look at today is the acetoacetic ester synthesis. Okay? So two kind of, big names, but we'll see that these are very easy reactions. Okay? So let's do a review of the malonic, and then we'll come back and do the acetoacetic. Okay? So let's make up another one for the malonic ester synthesis. Okay, so there it is. Two carbonyls, and both sides are esters, so that when we react this with base, okay, that takes off the middle proton. So we get our enolate ion, okay, so the lone pairs on the middle carbon. And then remember what we did is we alkylated that. So for example, let's bring in ethyl bromide. Okay. And so that'll put this ethyl group here. Note in this structure, I'm simplifying, I'm abbreviating this ethyl group as ET, okay? So not the movie ET, but an ethyl group. Okay. And then lastly, we took this and heated with H3O plus. Okay, so remember what we do at the end, we take one of these ester groups, we kick it off, and the other ester group turns into the acid group. Okay, and so we end up with something like this. Okay, so we get a carboxylic acid. Okay, so this was the whole setup of the malonic ester. Okay, so it gives a final product of a carboxylic acid. Okay. Let's go on to the second one, the acetoacetic. We'll see it's very, very similar, just one little change, okay? Just one little change.
I have a quick question.
All right, question.
Okay, you know how the middle CH is just, there's just one hydrogen on it? When we get our product, we have to change that?
Yeah, good question. So, yeah, you see here it's a CH and it becomes a CH2. We didn't go through the mechanism, but where it gets that extra hydrogen is from H3O+. Yeah. Okay, so let's do the acetoacetic. The difference is the starting material, okay? So I get to erase, you have to draw it all over. So let's make this here number 2. And what we're going to do here is leave one ester on, and on the other side, we'll have it as some kind of ketone, okay? So we have a ketone on that side. Okay? So, again, all I have to do is erase, but you have to redraw all this stuff. Okay, so the first step, exactly the same. Okay? Except again, I'm carrying a ketone on that side. Note it took the middle hydrogen, not this hydrogen, because remember, the middle one was more acidic because of the double enolate that could form. Then the second step, we'll go ahead and alkylate once again. So let's go ahead and put on an ethyl group, okay, like we just did. Okay, so now we have alkylated that middle alpha carbon. And then we'll do our last same step where we will heat with H3O+. Okay. So can we predict what's going to happen? Well, I got this ester group. What do you think we're going to do with that ester group? Okay, we're going to kick it off there. Okay, so this time we only have one ester, okay? So we're going to kick it off and just leave what's left behind. And what's left behind is that there. Okay, so you have these 3 carbons attached to the carbonyl, and then that CH3 on the other side. So here we end up with a ketone. Okay, so the acetoacetic ester gives a ketone for the final product. Okay. Any questions on that one there? Okay. two reactions that you want to keep in mind. We're going to come back to these toward the end of lecture, okay? And see another way to use them. All right, well, let's move on from this point. Let's come back and talk a little bit about the beta dicarbonyl compounds. Let's look at this diester here. And let's compare that to this one. And this diketone molecule. Okay. So you might say, well, what are you trying to compare? Okay, obviously they have two different structures, but what do you want to look at? Okay, what I want to look at here is I want to compare the acidity of those alpha hydrogens. Which one is more acidic? This one or this one here? Okay? How are we going to figure that out? What do we want to draw? The conjugate base. Okay? So let's take off one of those hydrogens. Okay, take off an alpha hydrogen on each there and draw the result. So there's the top one, give you the middle enolate. And there's the bottom one to give you that middle enolate. So what do we want to ask at this point? Which is more stable? Okay. So which of these two is more stable? Okay. If I can predict which is more stable, then the one to its left was the more acidic. Okay. So which one of these two do you think is more stable? Any ideas? Can I draw resonance for this one? Yeah, up to the oxygen. Up to there. Can I draw resonance for this one? Yeah, I can draw it up to there and up to there. So now what am I going to do? They both give resonance, same resonance structures. Any idea? Okay, good. Okay, you're right. We got two oxygens here. What are these oxygens doing? Okay, yeah, they're electronegative, so they're pulling. What else do they have on them? We got lone pairs. So this lone pair is here, so you got established resonance here and here. See that? So this double bond's being used this way, but then I get this lone pair and it says, hey, I want to come in the game too. But this says, well, I'm already being used over here, so I'm not going to use you as much. So my resonance is not going to be as much here as it is down there. See that? So this one here will be more stable. See that? And so these hydrogens here should end up being more acidic. Well, what do we look at to see how acidic they are? pKa values. Okay, so this one here, we are looking at somewhere around 13. Okay, so it's a little bit more acidic than water. This one here should drop, and it does, to 9. Okay, this is more acidic by a decent drop compared to that one there. Okay? So, did that so that, you know, we can use things that we've been using, resonance theory and all of this stuff, to compare these two. Okay? Any questions on that analysis? Okay? All right, well, we got one more part to this chapter. Okay? If you're following your outline, we're going to drop down to number 18. Okay. So on number 18, we're going to look at something a little bit different here. We're going to look at the chemistry of alpha, beta, unsaturated ketones. Okay, so it's something a little different. Okay, do you remember what an alpha, beta, unsaturated ketone was? We had what? A double bond next to a carbonyl. Okay, remember that? So it's alpha beta because the double bond is between the alpha and beta carbons. Okay? So we want to do some chemistry on this kind of molecule. Well, in order to do chemistry on it, let's see if we can break it down and find some of the properties of it. Okay? So one of the first things you always do if you ever get lost is look for partial charges. Does this thing have any partial charges?
Yeah.
Okay, you got a dipole there. So you got your minuses and positives there. Okay. So, anything else I can do? Well, another tactic you can use is try to draw some resonance. Okay, so one resonance I can do is to move these pi electrons up to the oxygen. Is there anything else I can do with that structure? Is there any more resonance I could draw? Yeah, I got an allylic carbocation. Okay, so that's ABC. So I can dump into there. And so get that resonance structure. Okay. So these resonance structures help me to see the reactivity of it. Okay? So I already saw out of partial positive here, out of the resonance, I can have a full positive there and there. So what does it make those carbons? What are they going to be called? What would you call those? Carbocation. Any other word I could use? Starts with an E. Electrophilic carbons. Okay, so I got one here, and I got one here. Okay. What's the big deal if I have electrophilic carbons? What can I react with it? Starts with an N, a nucleophile. Okay. So here, a nucleophile can react there at either side. Well, what question might you ask then? What would you ask now? What would you ask?
I was just gonna say, how would they react?
Okay. Well, since you have two different sites, you might ask, which one will it attack? Will it attack on the left or the right? Okay? Well, here's the answer to that. Okay? Depends on the type of nucleophile that you have. Okay? So if we have a strong base as a nucleophile, okay, so let's call these sites here A and B. If I have a strong base as a nucleophile, it'll attack site A, okay, such as OH minus, CH3O minus, real strong. But if I have a weak base, it will attack carbon B. Okay? And it's the weak base that we want to use. Okay? So you might say, what's an example of a weak base that you want to use? Okay? We're going to use a beta dicarbonyl anion. Okay? Things we were just using. And when we do this, this reaction is given a special name. This is what's called the Michael reaction. Anybody know somebody named Michael? Okay. Well, it wasn't named after them. It was another Michael. Okay? So make sure you give credit where it's due. Okay? So let's look at some examples of this stuff. Okay, so let's look at this alpha beta unsaturated ketone. Okay. And now let's bring in our beta dicarbonyl anion. Okay. What we'll do is use the one that we used for the Malonic ester synthesis. Okay. So this is a weak base, so we're going to attack the beta carbon all the arrows will end up moving toward the oxygen. Okay, so this gets a little clumsy to draw. There is my CH, adding on the beta carbon. Okay. Now let's draw the rest on this side. Finish it out like that. the next step, what we do is we add H3O plus. Okay. I'll take you through the mechanism, but what it does is it makes this the enol, and then it goes through and makes the ketotonic. Okay. I'll let you look at your book for that. Okay, so you can see how a hydrogen will add here to make the enol, but remember that the keto is always the more stable one, so it reverts to that. So let's draw the product of that. That there. Okay, so this is the result of the Michael addition. There's one last thing we can do. Can you see what we can do? What do we have here?
2 esters.
2 esters. Let's do that malonic ester synthesis now. Okay? So let's add H3O plus in here. Okay, so I told you we're going to come back and use it. Okay, so follow along. He has a lot of pieces in there to draw. Okay, so since I'm a diester, I'll take one and kick it out of there. And the other, I'll make an acid group. So the result of that is this carboxylic acid here. Okay, and this final product is what's called a beta keto acid. Okay, because the acid group ended up on that beta carbon. So this kind of clumsy chemistry we did, this result of the Michael, is actually chemistry that goes on in your body. When you take biochemistry, you'll see how. Okay? Chemistry in pharmaceuticals uses the Michael reaction. Okay? So that's when it gets interesting. Just doing this stuff may get a little dry on carbon atoms moving here and there. But when you apply it to your body, that's when it comes to life. Okay? Any questions on that Michael reaction? Question?
Oh, no.
All right. Well, we'll give you one. See if you can do it. Give you a couple minutes, if you want to work in groups, see if you can figure out that one there.
Have a fun. Thank you.
You want to try to draw the product? No? Does anybody want to go up and try? And it's waiting for you. That's you, Mercedes.
Okay.
You want to try it? Give it a shot. Very good. Piece of cake. Piece of cake. Frosted Flakes. Rice Krispies. No, no, so I just, ask you to draw the final product there. Okay, so that added on, kicked off, the other group became the acid, and it added on to the beta carbon. Okay. Okay, here's the carbonyl, alpha, beta. Any other questions on that? Okay. All right, so that's the end of notes for the course. On Wednesday, we'll come and do review. Make sure you bring your textbook. Yeah, no quiz.
No.